Hi everyone. We're going to take the next 30 minutes and have a look at power quality monitoring, and more specifically we're looking at Qualitrol's offering, which is the Informa and the IQ Plus. The Informa is the hardware side, the IQ Plus is the software side. So let me just set this up to presentation mode and we'll take a start. So the things that we're going to cover are, we're going to take a look at the market drivers. We're also going to look at some of the basics of power quality. There are a number of standards that are involved, and we'll look at how that plays out across the world. Then we'll dive into Qualitrol products and the key features, and we'll get a little look at the IQ Plus software and maybe have a look at hands-on and how that's used. Our products, before we start, it's the Informa device, and there are two variations of it. There's a 9-channel and there's a 36-channel device. In between, there's 18 and 27. The software that goes along with that is called IQ Plus, and we'll get into both of those in a little bit of detail later on. So the market drivers. If we look at an overview of the grid and we break it down into transmission, sub-transmission, and then into distribution, most of our transmission users will be familiar with the fault recording aspect. So if we look at DFR records, if we look at dynamic system monitoring or slow scan and sequence of event recording, and these are based in around large disturbances that happen at the transmission side of the network. We also have this phaser measurement units installed at various nodes in the network, and that's looking from a wide area point of view. We could bring in fault location, either impedance using the DFR record or traveling wave fault location. It tends to be at that transmission and sometimes the sub-transmission portion of the network. If we look down to the distribution, there is another aspect that we need to look at from a grid monitoring point of view, and that is power quality. Now, power quality does go right down to the house level or the residential level, right up to 30 kV, and even at times into the 150 kV or just sub-transmission. And we're going to take a look at that from that aspect. The market drivers, again, we break this down into three different portions. The first portion is it's internal system planning, and this is where the utilities are looking at asset early life failures or plant trips or unusual disturbances, and they may find power quality as a help to try and understand what's going on. There are no obligations to install PQ in this particular aspect. The second one is customer complaints. Now, some customers, large industrial plants or even right down to residential, may complain of the quality of the power. These are complaints or sensitive customers. We may end up moving those to different feeders, but again, there is no obligation at this point to install power quality devices. However, utilities do, and they tend to use portable PQ devices and move them from one place to another, looking for different aspects of quality issues in the power. And then the third one is the regulation of PQ, and this is where utilities in different regions in the world are obliged to install power quality monitoring. There are compliance reports that they have to submit to the regulator. There are PQ standards in place, and that takes part in quite a number of locations around the world. If we took, for example, in Europe, there is a burden of proof required in Europe, where if there is a power quality issue, the utility has that burden of proof, and they use a standard and a report out, which is the EN 5160, and they use that to show whether their system is providing good or bad power quality. If we looked to other regions in the world, so we talked about Europe briefly, there is PQ regulation. There is PQ regulation In South America, it's through what's called the Craig reports. There's not so much regulation in North America, so it's driven mainly by customer complaints and fault investigations. South Africa has regulation, Australia has regulation, and in other regions in the world, it's mostly driven by customer complaints and sort of fault investigations and looking at early life failures and why. So you can see it's different. Different regions of the world have different reasons for adding power quality monitoring to their systems. The task really for a utility is to find where the power quality is coming from, and it tends to be loads on the network that are causing it. So, such as vehicle chargers or LED streetlights, other types of load like smelting plants or the various industrial plants that can cause the quality of the power on that feeder to be diminished. And it's up to the DSOs to try and identify those problem locations. There are other things that are happening on the grid that are increasing the amount of poor quality on the network. And that is mostly in relation to addition of distributed energy resources. So as wind or PV is being added onto the grid, these are adding power quality issues like harmonics or voltage instabilities or frequency problems. Most of the harmonics are being introduced by inverters. So there are power coming from these plants and it has to be inverted and added onto the network, and it's introducing harmonics and other problems. So that's happening all around the world, and it's increasing the focus then on power quality as a measurement method and looking for issues on the network. When we come to measuring those, there is a lot of manual hunting down of the problem. Where is it occurring? What parts of the network? Sometimes we're using portable devices and moving from one place to another. The data that comes from these devices is a large amount of data, and it takes resources to look through that data and try and figure out what's going wrong and where, and it can be expensive and time consuming. But there is a better way, and we have Qualitrol's flagship Informa and IQ Plus solution. It is certified Class A. It can generate all the various reports that are required for compliance in various regions of the world. What's more, these reports and the data can be stored for beyond a year, and utilities are using these to find out root cause and then countermeasures. And this is changing all that data into the information and presenting it in an easy to understand format. So let's have a look at the power quality basics. There are essentially two categories that we can put power quality into. There's the steady state and non-steady state. If we look at steady state, and by that we mean continuous recording. So we're looking at calculations like power, like voltage, flicker, harmonics, unbalance. And what we're doing on our system is every 10 minutes, we are taking a sample of all of these calculations. And in fact, there's well over 1,000 calculations per circuit that can be performed by these PQ devices. So every 10 minutes is taking one sample. And then it's storing all those in the course of a week or a month or a year, and a customer can look back in the long-term trends of that data on his network. The second one is non-steady state, and this is where we're triggering a device to create a recording, and it's mostly based on dips and swells and interruptions. For power quality, we're mostly looking at the voltage too, although we do look at harmonics with regards to this continuous recording and current, sorry, what I meant to say is currents on this continuous recording. We look at other things in triggered recording as well. So rapid voltage changes and voltage transients are all wrapped up in this non-steady state and triggered recordings. So let's dive a little deeper onto the continuous recording. So here's an example. As we mentioned, continuous recording is a sample every 10 minutes. There are well over 1,000 per circuit. And in that one sample, what we're actually doing is it's 3 calculations. We're taking the maximum value that calculation was in the last 10 minutes, the minimum value, and then the average over that 10-minute period. And on screen here on the right-hand side, a little difficult to see, but that's voltage, red, yellow, blue, and we've got frequency at the bottom. The middle trace is the average, the red here is the average, and then we've got grey on top is the maximum, and grey on bottom is the minimum values. And you can come to see there's one portion here where the minimum dropped quite low in comparison to the rest, and the average and the maximum stayed quite steady. So that's a continuous recording example. If we looked a little bit further and discussed the RMS voltage and RMS currents, here's what it would look like over the trend of a 1 week period on an industrial plant. And in fact, these are the signals that are coming into the Belfast plant, the Qualitrol plant in Belfast. Down at the bottom, we've got our currents, and at the top we have our voltages. And what we see here is the currents in the evening, it's dropping off, and then in the morning around 8 o'clock, people are coming into the office and the current and the load is increasing. So it increases over the course of the day, in the afternoon and the evening starts to tail off again, and then at night time. So that's potentially Monday, Tuesday, Wednesday, Thursday. If we zoom in on this, we're zooming in on a voltage here. You can see each notch is a 10-minute sample. So every 10 minutes we're adding one more sample, the maximum, average, and minimum. Now, if we were thinking of voltages, what we're really looking for are variations in those voltages being caused by load variations or switching events. And we're looking to see how that pans out over the course of a long period of time. Another calculation that we do on continuous is unbalance. And here we're looking to see the 3 different phases, A, B, and C. They should be 120 degrees apart. They should be the same size and magnitude as well. If that changes, if we have a change in magnitude and a change in phase angle, that is now an unbalanced 3-phase system. And most of the sources of this are single-phase loads on a 3-phase circuit. So utilities are looking for this unbalance and trying to correct for it. Another calculation that we look for, which is quite important in power quality, is harmonics and interharmonics. And again, it's a 10-minute interval. So in the harmonics side of things, we can break this down into the harmonics up to the 50th. And you can see the second and third. The third harmonic in this particular trace is looking around 3%. The fifth harmonic is looking around 4%, 5%, and then it tails off to all the other harmonics right up to the 50th. There's next to no 50th harmonic in the overall content. And we know that harmonics can be damaging to equipment on the network as well. So like unbalance, unbalance can cause extra heating in transformers. Harmonics are something similar. So people may look at a transformer and try and gauge the rating of a transformer, but not take into account harmonics, which will cause the transformer to be pushed even harder than it's supposed to be. So these can have damaging effects on other equipment on the network. Another calculation we look for is power frequency. Now, power frequency is a 10-minute sample, but in this case, there's also a 10-second sample. And here we're looking at that frequency and how that changes in relation to generation on the network and load. So we're always balancing the generation to the load. If the load disappears, the generation initially speeds up because there's no load holding it back, and there's a bit of inertia there. There are lots of oscillations that can happen on the network where different parts of the network are generating different generating plants, and then load balancing and oscillations can occur which can cause damage to generating plants. So there are things that we're looking at here on power frequency. We also look for what's called flicker. This again is a 10-minute sample, but there is another 2-hour sample that can be looked at from a really long period. And here it's a fluctuation of the voltage, and that fluctuation of the voltage appears to a human as a light bulb that is flickering, and that's why the term flickers has come about. It is only an issue for humans. It has no real effect on the electrical network itself, but if you're sitting in a residential home and you've got light flickering at a certain frequency, it can cause headaches and other problems. So it is measured as a power quality, and down below, these are the two traces. One of them is a 10-minute average. 10-minute sampling, and the bottom one is a 2-hour sampling. And in flicker, in the case of it going above a particular value, there are thresholds where if it goes too high, it's considered it's considered flicker that is damaging or hurtful to the human as they sit in a room with the light flickering. The last one on continuous recording is main signaling. And this is something that we look for. There are artificial signals that get sent across some of these power lines, and these artificial signals we monitor for that as well, and it's used generally for switching on and switching off equipment or changing tariffs. So these are 3-second sample rate. It's quite different from the other continuous, but it's something again that we record in our Informa device. So let's take a look at triggered recording. So triggered recording is slightly different. This is where it's looking at the actual sine wave, and we're looking for dips in voltage or sags, depending on what region of the world we're talking. Some regions call it dips, some call it sags. And then there's also swells. So we could have this voltage actually swelling higher. So we're looking for these dips or swells, and we're trying to gauge how far did it dip and how long did that dip last for. And depending on how far it dips and how long it lasts for, it can damage equipment like PCs or large server rooms where there is sensitivity to these voltage dips or swells. So when that happens, that's a triggered event. And that triggered event, what we record in power quality world is the RMS value. So here is what it normally is, around 100%. And then it traces close to its normal value, and then it dips down below the normal value, stays below that value, and then eventually recovers back again. That time is what we're measuring, and the percentage dip of how far we're also measuring. Depending on how far it dips and how long it dips, there are damages that it can do, as we mentioned, to PCs or server rooms or other sensitive electronics. The causes, they tend to be faults on the network, maybe a motor starting or some transformer being energized, or sudden big load changes, and they can all cause this dip to happen in the voltage, which can cause damage to electronic devices. So how does this all correlate together in the data? If we think about grid monitoring and the whole analysis of the functions and features across a grid monitoring system, what we have on screen here is our slow scan recording from a fault recorder. So in slow scan recording, we're sampling either 50 samples per second or 100 samples per second. We look at calculated value like RMS voltage or RMS current or three-phase power or harmonics frequency, and different calculations on the voltage as well. These tend to be minutes in length. This one here we've actually shown is a 10-minute segment of that, and that's continuous recording in a fault recorder. It's called dynamic disturbance recording, DDR. If a fault happens on a network, we also take a segment of that slow scan recording and we call it triggered. Dynamic disturbance recording triggered because it's being triggered by an event on the network. At that same time, that triggered event creates a fault record. And here we've got our three-phase voltage, three-phase current. The fault happens at the time of that fault, the current goes high, the voltage drops. And here, what we have, and if we refer this to the power quality world now, that same disturbance is viewed in an RMS envelope. So rather than looking at the raw sine wave, we've calculated the RMS values, and we can see that it dipped this amount for this length of time. So that's the triggered recording, as we talked about. The continuous recording in power quality world, there are actually a couple of variations of it. There's a free interval, which we can configure as long as we want. In this case, we're probably configuring it for 20 seconds or less, and that free interval is something that we can set from anything from 200 milliseconds sample rate right up to 24-hour sample rate. This is not required by the standards, but it's something we get for free when we're doing PQ calculations. So here you can see how it's taking a sample. In this case, it's probably every maybe every 30 seconds or so, and it builds all of those up as samples. And then the last one is this 10-minute sample that we talked about, which is required by the standard. So that whole segment here, for every piece of this segment, we'd have one sample which shows the maximum and the minimum and the average of all of those calculated values. So that's how it all ties together, from fault recording right through to power quality. There are PQ standards, and our devices are compliant to all of these standards. The 40-30 talks about how to test and measure. The 40-15 again is testing and measuring. In this case, it's flicker, and then there's some testing and measuring in harmonics and interharmonics. These standards don't give limits, however. It talks about how it should be recorded and tested. So it's all about the measurement techniques themselves. How often do we sample? How does that sample get built up into a 10-minute segment? And these are international standards that we are compliant to. Then there are other standards like the reporting side. This is an EN 5160 report that's generally used in Europe, but has also been adopted in other regions around the world. And here they're looking at thresholds, and it's on a per week basis. So rather than getting into all the detail of what happened during the week, it's filtering all this into a 1 week period and telling us whether we're good or bad. It does define the limits, and it defines it for low voltage and medium voltage portions of the network. So if we take a look at compliance, we have talked about the burden of proof. Are we within thresholds or not? One way of looking at compliance is looking at the serve on a table tennis. When it comes to serving a ball in table tennis, we have to bounce in one square on one side of our net, we have to cross the net, and we have to bounce in a square on the other side of the net. And these are requirements. If we expanded this out to 100 shots, and we decided these are the things that we're going to look at: a proper service, the ball touching the net but not bounce, the ball staying in the net or completely miss the table. And if we decided these were the numbers that we found happened after 100 shots, this is what the coach was expecting. So expecting greater than 70% proper service, less than 20% touching the net, etc. In this particular case, all of these shots are non-compliant. So in 100 shots, only 50 have met that coach's expectation. And that, if we did it again and we ended up with 80 shots going over the net with proper service, bouncing on both sides, and 18 didn't, 18 hit the net, balls touched the net but not bounce, it's less than our coach expectation. So we are now compliant, and those can be applied equally to the measurements that we're talking about in PQ world. So we've got dips, swells, and interruptions, and they could be measured in that same way. And that's simply how we measure compliance with regards to the triggered recordings, the parameters that we're looking for, and the compliance thresholds that are set. So the EN5160 sets those thresholds and the parameters that we need to look at. One of the methods to help that more visual is by using curves that we call CBEMA, the SARFI curves. And I guess let's take a look at them to try and explain. This is actually a CBEMA curve, and every dot on screen is either a dip or a swell or an interruption, so it's a triggered recording. The curve at the top is telling us that anything that falls above that curve is outside of compliance, and anything that falls below the bottom curve is outside compliance. Anything that stays in this region in the middle is in compliance. Now let's take a little look at what's happening here. What we're saying is this 100% is our normal voltage level. So we're 100% is normal. If we swell above 100%, it can go up potentially up to 390% of that normal value. Or if we dip below, we can go right down to obviously 0, which would be an interruption. Across the right hand or the x-axis, we have the time. So we're talking 100 microseconds, 300 microseconds, right up to 13 minutes. Really what we're saying is we can swell as high as we want, as long as we don't last any longer than, say, 50 microseconds. And again, we can dip as long as we want, as long as that dip doesn't get any longer than 8 milliseconds. So it defines the swell, the dip, and the time, and it becomes easy at a glance to see, well, okay, we've had 1, 2, 3, 4, 5, 6, 7, 8, 9 instances on this particular curve. 3 of them are compliant, one of them is just right on the edge, and the other ones here, one swell was outside of compliance, and the other 3 were interruptions which are outside of compliance. So these items here can then damage any electrical equipment, any electronics that's connected to that portion of the network. And it's just a really nice way of seeing at a glance what's going on with regards to dip, swells, and interruptions. Okay, so let's take a look at Qualitrol products. Now, the Qualitrol products do everything that we've talked about so far. If we look at the hardware side, there is a 3U device, there is a 6U device. The 3U device can take 9 analog channels. The 6U device can take up to 36 analog channels. And what I've highlighted in red here is one of the most important parts when it comes to the hardware side. One single Qualitrol device can monitor 10 circuits, and this does save a lot on installations. Most of our competitors are able to monitor 1 circuit at a time. Maybe some can monitor 2 at the most, but in our Informa device, we can monitor up to 10 circuits on 1 device. These devices are compliant to the Class A PQ. It does harmonics up to the 50th, does flicker, unbalance, sag, swells, interruption, all of the things that we've talked about so far. It also does a version of a fast transient recording. This is where we're sampling up to 20 megahertz, and it can look for some of these really fast transients that occur in the network. Points of difference from our competitors. We have a large saving on the analytics in the way that we present the data into information. It saves an awful lot of time on trying to figure out where the problems are. We have a software which is client server. It means for easy access and less information required to get to the problem. We're Class A compliant. We have some favorite that are single click shortcuts. Again, gets faster analysis. The system is easy and quick to install. And we have an overview page that you can see a full fleet of devices at a glance. And we'll take a look at that in some of the next screen grabs. The software itself. So the software, we call it IQ Plus. It's our master station software. Here are a couple of screen grabs from it. But that one software can talk to hundreds of our devices. And again, this is another advantage over some of our competitors. We have that software. It can be used to configure, pull back data and display data from hundreds of devices out on the network. This is what the software looks like. On the left-hand side, we've got our devices. In the middle is where it shows the data. In this occasion, there's nothing showing at the moment. On the right-hand side are a number of these favorites. Along the top, we've got our ribbon tab, very similar to most Windows applications. So we can click on triggered recording, continuous recording, or the overview. And then down at the bottom is where we've got the communication back and forth to the device so that we can see what's going on with the software. One of the things that we can do, which helps gather the data itself, is we can set up scheduled actions. And here what we're telling the software to do is go to each device in the network and pull back all of this information and do it at a regular cadence. So we can set it up for every 24 hours or every hour or even faster. And once that's set up, we can walk away from the software. It will, every periodic time, go to all of the devices and pull back all the relevant information that we need. And when we have any issue, we come to our software, we take a look, the data is all there automatically. We don't have to go searching for it. And this is what the main screen would look like from a power quality overview. Here what we have is all of our devices listed down the left-hand side. We have across the top the parameters that we're monitoring. So we're monitoring events which are triggered dips, swells, and interrupts. It's below dips, swells, and interrupts. We're looking at our voltage, RMS. We're looking to see is it compliant or not across the three phases, L1, L2, L3. We're looking at total harmonic distortion, flicker, and lots of other things, and we can add and remove pieces of information to that. And then down below that, each square then represents whether that calculation or event is compliant or not. So you can see we've a couple of dips here. It's still compliant because it hasn't crossed the overall threshold for dips. There are some green squares for the RMS voltage for that particular substation, but you can see at a glance here there's two red squares where this substation and this calculation, there are issues with the system out of compliance. And this screen itself is a real powerful screen because it's not just showing at a glance. Each of these squares are clickable squares, so we can see at a glance, but we can also dig down. If I come to the next screen and we take an example, in this we're looking at one individual device, and we can see that the dips, there are 16 dips, and that's gone through a threshold of compliance. It's marked it as red, but a user can double click on that square, and that opens up then a list of all of those dips, swells, or interruptions. In this case, they're all dips. They can also then dig a little bit farther, so they can right click on any one of these and select open, and we can click on open RMS envelope, and this is where they get to here. So now they're saying how far did that dip and how long did it dip for. And it's, if I click back, any one of these squares can be clicked in that same way. So we see our overview to begin with. It's easy to figure out where the problems are. And if we dig down in, click on any one of those squares, it loads up that information. Another piece in the software which we look at are reports. And this is where we're looking at an EN5160 report, and this is automatically generated every week. So you can see here back on the 14th, it's 2 buzz bars, and then on the 21st it's reported, and then 28th reported. So every week it's reporting, or it's generating this report. But what it's also doing as it generates it, it's marking, has all of those calculations that we're looking at, were they compliant in the week that just passed? And it will mark it as yes in black, or it will mark it as no in red. And like the green and red squares, these are all clickable. If someone clicks on that, they will open up a compliance report, and here it lists all the calculations that we're looking at, and it marks it whether we're compliant or not. So these are all of the quick methods of changing that data into information. On the continuous recording, what we have on the right hand side is all of these preset favorites. So I can click on voltage RMS. It will list that voltage RMS for this time period that we selected, and you can see these are currents, these are voltages, and you can see each day as users come into the office and leave the office the trace of load. We can click on any one of these other favorites on balance, power, we got harmonics, we got single phase, PQ overview, interharmonics, and they're all, as we click on it, it just populate this screen to take a look at the detail. This is the one we've already covered, triggered recording, but there's not just this one graph that we looked at, or chart. There's charts that can help us identify where the problem areas are. And that brings us probably to the end of a high-level overview of our PQ devices. There are many different reports, custom reports that we can generate and have those automatically sent to users that are requiring the reports. And it just makes for an easy to understand. There is so much data involved in PQ devices, and making it understandable at a glance helps save so much time in getting to the problems and correcting them as quickly as possible. So I hope that helps highlight Qualitrol's offering on PQ, and we'll try and do this again with some other features in Qualitrol's products. Okay, thanks very much for listening.